Hey, welcome back. Here's another example. This one again in 3 variables where we're going to perform this Lagrange method, this Lagrange multiplier process for constrained optimization. The objective function is a linear multivariable function, x plus 2y plus 2z. Looking for the largest we can make that function, subject to the constraint x squared plus y squared plus z squared is equal to 9. Our step 0 was to put our constraint in standard form. So we have x squared plus y squared plus z squared minus 9 is equal to 0. And that means our function g of x, y, comma z, it's 3 variables, so I need the z there, is just that, x squared plus y squared plus z squared minus 9. Now step 1 is we're going to construct capital F. We're going to make F. So capital F is equal to little f plus lambda times g. Little f is our x, in brackets, not multiplied by anything, so x plus 2y plus 2z plus lambda times our constraint, x squared plus y squared plus z squared minus 9. Now we do step 2, make the system of equations. So we take the x derivative, we get 1 plus 0 plus 0. Oh, and I forgot again. Let's simplify. Simplifying just means multiplying lambda through the bracket. Lambda x squared plus lambda y squared plus lambda z squared minus 9 lambda. So we take the x derivative, we get a 2 lambda x from this piece, and then zeros for the rest because they don't contain any x. Our y derivative, we get 0 plus 2 plus 0, 0, and then 2 lambda y. The rest are zeros. Our z equation is just like those ones. 0, 0, 2, 0, 0, 2 lambda z. And then our f lambda equation is free. We get x squared plus y squared plus z squared minus 9 for that lambda derivative. And we set each of these derivatives to 0. I'm going to rewrite the system in a cleaner form. So the first is 1 plus 2 lambda x is equal to 0. The second is 2 plus 2 lambda y is equal to 0. The third, 2 plus 2 lambda z is equal to 0. And the last one is the constraint x squared plus y squared plus z squared minus 9 is equal to 0. Let's see. So I'm not quite sure what the best method is how to solve this. It might be best to isolate the first for x, the second for y, and the third for z, and substitute each of those x, y, and z into the third equation. That will give us an equation in terms of lambda. We can get the lambda value and plug that lambda value back in to find x, y, and z. Or it might be easier to get, let's say, y in terms of x and z in terms of x. And then we get one equation just in terms of x. So I'm going to do it that way because it's the most familiar. It's the most similar with how we've already been solving these problems. So next, get y in terms of x and z in terms of x and sub into f lambda is equal to 0 equation. So I'll do that in the next slide because this is going to take some space. 1 plus 2 lambda x is equal to 0. 2 plus 4 lambda y is equal to 0. Let me double check that. Oh no, it's 2, not 4. Okay. 2 plus 2 lambda y is equal to 0. 2 plus 2 lambda z is equal to 0. X squared plus y squared plus z squared minus 9 is equal to 0. So in the first equation, actually in the second equation, do some isolating. I'm going to get lambda all by itself. We have 2 lambda y is equal to negative 2. Then divide both sides by 2y. So lambda is equal to minus 1 over y. And for the third equation, we'll do the same thing. We have 2 lambda z is equal to negative 2. Divide both sides by 2z, so lambda is equal to minus 1 over z. Number of the equations. If we plug that into the first equation, lambda is equal to minus 1 over y, we get 1 plus 2 times minus 1 over y, x is equal to 0. So that means 2x over y, 1 is equal to 2x over y, just adding that block to both sides. So that means y is equal to 2x. Cross multiply. We can take that other equation, lambda is equal to minus 1 over z, and also plug it into x, plug it into equation 1. So we get 1 plus 2 times minus 1 over z times x is equal to 0. So 1 is equal to 2x over z, and then cross multiply, so z is equal to 2x. And then we plug those two into the last equation. The reason we did all that was this now makes this last equation an equation of one variable. We have x squared plus y squared, y is equal to 2x, so plus 2x all squared, plus z squared, 2x all squared, minus 9 is equal to 0. So x squared plus 4x squared plus another 4x squared minus 9 is equal to 0. Add up all the like terms. 9x squared is equal to 9. So x squared is equal to 1. We get two solutions this time. We get x is equal to 1 and x is equal to negative 1. For the first solution, if x is equal to 1, then y is equal to 2 times 1, which is 2. Z is equal to 2 times 1, which is also 2. And then for the other x solution, x is negative 1, y is equal to 2 times negative 1, which is negative 2. And z is equal to 2 times negative 1, which is negative 2. So we get two special points. Put it all together. We get the first point, 1, 2, 2, and we get the second point, negative 1, negative 2, negative 2. Now we do the last step, which I forget what number we're on. Step 3, evaluate our objective function. We're going to evaluate it at those 2 points. Can't remember what the objective function is. X plus 2y plus 2z. So f evaluated at 1, 2, 2. That's going to be 1 plus 4 plus 4, which is 9. F evaluated at minus 1, minus 2, minus 2. So negative 1 minus 4 minus 4, which is negative 9. Now recall your methods for finding global max and global min for prior calc course. So you took all your special numbers, plugged them in to the function, plugged the boundary into the function, and did a comparison. And here, we only have two numbers to compare. We have a positive 9, we have a negative 9. One of them is the local, or one of them is global max, one of them is global min. The largest one is the max, so global max at 9, or of 9 at that point, and global max of negative 9 at the other point, global min at the other point. And we're asked to maximize it, so that would be this one. That was the ask, that was the question. Now, last example to go through for this week's videos. We have a multiple choice question that's a partial problem. And these are much better preparation, because doing the whole problem from beginning to end, if you make one small mistake, everything goes sideways. Whereas a single piece of the question can be tested with less risk that everything will go bizarre and you'll get lost and stuck and wasting time. So this one asks to use the method of Lagrange multipliers to maximize the function xy plus 10 subject to that constraint. It tells us we must solve this system, and then it asks not to actually solve the system, it asks us to select all the candidates for points which maximize or minimize this function subject to that constraint. And there's two approaches. One approach is to actually solve the system. The other approach is to test each number. I'm going to write that down. So method A, sub each point. Problem is, actually I'm going to start writing it down and I'm going to erase it because I don't want someone to read the notes and not see the video and then try to make sense of the note without the explanation. What we will run into if we try to substitute each point into the system is we'll run into not knowing what lambda is equal to. We'll have to make sure that lambda is a consistent value in each of those three, in those first two equations, for any point that satisfies the third equation, any point that satisfies the constraint. So it gets quite messy. It's not something I suggest. So I'm going to stop writing down method A and go right to method B. Let's just solve the system. So I'm going to number the equations so they're easier to refer to. From equation 1 says that 2 lambda x is equal to negative y. So I'm going to rearrange that, divide both sides by 2, and divide both sides by x. So lambda is equal to minus y divided by 2x. Then I'm going to sub that into equation 2 and see what we get. So equation 2 is x plus 18 lambda y is equal to 0. I'm replacing the lambda. X plus 18 times minus y over 2x times y is equal to 0. And then simplify. X is equal to, I get 9y squared over x. So adding that block to both sides, y times y is y squared, 18 divided by 2 is 9. I'm going to cross multiply. So x squared is equal to 9y squared. Now I'm going to plug that into equation 3. So we had in equation 3, x squared plus 9y squared minus 18 is equal to 0. I'm replacing the x squared with a 9y squared. So 18y squared is equal to 18. That means y squared is equal to 1, and we get two solutions. Y is equal to 1, and y is equal to negative 1. From the first solution, we can get the x value. X squared is equal to 9 times y squared. Y times negative 1 squared, so x squared is equal to positive 9. And that gives us two solutions. X is 3 and negative 3. And then the next one, if we check y is equal to positive 1, we have x squared is equal to 9 times positive 1 squared. So x squared is equal to 9. That also gives us those same two solutions. X is equal to 3 and negative 3. We got to put it all together. We got to combine them. So we have the x comma y for the first set, 3 comma negative 1. And negative 3 comma negative 1. And then we have the second set, 3 comma positive 1, and negative 3 comma positive 1. And do we have one of those? Yes, we do. We have option D. And that's it. So the question just wanted to know what the critical numbers, or not critical numbers, what the special numbers were. And we did it by using a process of substitution. And I mentioned that we can check, we can confirm which are potential locations for max or min by checking which ones satisfy the constraint. And then if they satisfy the constraint, making sure that we get a consistent lambda value from the other two equations. Notice that in option A, that the first number, the first point that's proposed, 0, 0, does not satisfy the constraint. If you replace x with 0 and y with 0, you get 0 squared plus 9 0 squared minus 18 is equal to 0. So you get negative 18 is equal to 0, which is not true. So that point 0, 0 definitely does not fit. You can cross out A. And you can try the next one. At 1 squared plus 9 times 3 squared. So 1 squared plus 81 minus 18, that's not 0. You can cross out option C. That means you can cross out option E. How about option B? So root 18 squared. Yeah, that one works in the first equation, the next one. But then it's a problem. The root 2 is also, so option B is very tempting. Option B satisfies the constraint. However, it's not going to give a consistent lambda value inside equation 1 and equation 2. So it's very dangerous to use that method to include or to show that the point is where the max or min is. But that method does work for excluding points by throwing them only against the constraint, making sure that those points are on the constraint, make sure that they're on the boundary. If they're not on the boundary, they can't serve as locations of a global extrema on that constraint. So that's it. Just as a warning, I did say that we are solving for the global extrema, and that's true. We're solving for the global extrema on the boundary, on that constraint. There might be a tall mountain somewhere in the interior of the function. This method that we are using does not find that. If we wanted to look for the true highest point of the function subject to the constraint, which includes the interior of the constraint, we would have to combine both methods that we've learned inside this course. We would have to do the capital D thing. We have to look for critical points of the objective function, setting fx and fy to 0, not dealing with lambda. Solve that. Get the critical numbers. Plug them into into the capital D function to check those critical numbers are max or min. If they're max or if they're min, plug them into the objective function to check the output. Then compare that output to the output we would get for these. That would give us the true global max and global min in the interior of the domain and including that domain, including that boundary. So we're not going to do that. Likewise, we're not going to do the case of multiple constraints. There's so many extensions that are possible for this type of optimization. We stop here. This is just meant to give you a taste. It's meant to be introductory. And that's the end of this component of the course. We'll start something very different next.